All right, let's see. I'm recording. All right, let's begin. Let me just make sure this is correct. Okay, that looks good. All right, so we're gonna continue with our calculus lessons. We just got into derivatives, and now I said last time we're gonna start derivative rules similar to the limit rules, where if you have a sum of two series or two functions, then the limit, if the limit exists for the individual functions, you can usually just add the limits. Or, product of functions, if the limit exists, then the product of the limits also exists usually. So this is similar, but for derivatives. And let me get my pen. What should we use? Blue or black? All right, let's go with black. So this will be lesson 9 on derivative rules. I might have to switch to a different marker soon, but okay. So the first rule is pretty standard in calculus. It's called the power rule. So if you have x to the power n, we want to know what's the derivative of that function. All right, so power rule. And there's usually two common notations for a derivative. So we have this d over dx. This is all just notation. Everything just means, the derivative always just means the limit definition, but this is just notation, so we don't have to write that limit every time. So d over dx is the derivative of the function x to the n. And the power rule says that this is equal to n times x to the n minus 1. So power rule says basically if you have x to the n power, you want to take the derivative, it's just n times x, and then you lower the power by 1. So you have this n minus 1 rule here. All right, and I wanted to prove this since the proof is kind of interesting. Of course, we haven't really learned much, so we're just gonna prove it by definition. And the proof goes, basically you just want to expand x to the n in the definition of a limit. In the definition of derivative, which involves a limit. So it's a limit as h goes to 0. And now we're going to plug in x plus h into the function. So it'll be x plus h to the n power minus x to the nth, which is just plugging in x. And then divided by h. This was our definition of a limit, right? It's the function to the n minus, x plus h plugged into the function minus just x plugged into the function, right? After we step some small h amount. And then we take the difference of these two and divide by h, whatever that small number is. And really this whole problem just comes down to how do we expand the x plus h over here to the n using binomial theorem, or binomial expansion sometimes it's called. But basically there's going to be some polynomial x plus h. If we multiply that all out, we would get some polynomial in x and h. And the binomial formula basically tells you what the coefficients are. We need these n choose k coefficients. So we can rewrite this limit. This to the n power is actually just a sum by the binomial theorem, or binomial formula. So this is a certain polynomial. It's I starting at 0 to n. We do n choose I, and then it's x to the I, h to the n minus I. Okay, so basically this is a bunch of notation. This right here is just the n choose I. So this is the coefficient in the binomial expansion. I would just suggest, if you're confused by this, just pause the video and do a quick Google search for the binomial expansion formula and the n choose k coefficients for that. So that's what this n choose I here is. That's the coefficient. So we have x to the I times h to the n minus I. And basically we just want to delete the terms that are x to the n, because there's an x to the n over here and an x to the n on the right. And then we're going to look at all the terms that we're going to factor out an h basically from the remaining terms and then just divide by it. Okay, so I'm running out of room a little bit here, but I'm going to erase everything and we're going to rewrite what this is. And we're going to show that this limit actually exists and it's what we want it to be. Alright, so basically again we're trying to prove this n times x to the n minus 1 is this limit right here that I just put a square around. So we're going to erase everything and we're going to show that this boxed thing equals this. That this limit is actually just equal to n times x to the n minus 1. And basically the reason is that there's an x to the n here that cancels with an x to the n here. And yeah, you'll see in a second. Okay, so really, if we want to rewrite that sum we had, there was an x to the n plus n times x to the n minus 1 times h. Then there was a bunch of terms that all contain h in them, so I'll just put it like that. And then there was a minus x squared at the, or x to the n at the end. And I'm purposefully being vague here about what's multiplied by h here. I kind of want you guys to do this on your own if you're following along. So try to figure out what the blank would replace here, that it's h times something. What is the h? I'm basically factoring out an h from everything else, all the other terms. But you can get all the other terms from that binomial expansion formula. So if you look up that formula and you try to figure out what are all these other terms, you can figure out what they are. They have, some binomial coefficient in front of them, right? Like the next term, if we're counting down here, it would be like x to the n minus 2 times h squared, and there'd be some coefficient here, right? But here, so I've purposely written it this way because we know that h, or really it's h squared here times something. Because once I divide by h, I'll still have an h here, and we know that the limit as h goes to 0 of some polynomial, it'll just be, we can just plug in the value because the polynomial is continuous. So really, we can say this whole limit is equal to, oh, and of course the x to the n here, and we have a minus x to the n over here. So it's really the limit as h goes to 0 of n times x to the n minus 1, and then you cancel the h, plus, and then this was h squared, and we're going to cancel one of the h's, so it's h times something. And this something is a polynomial. It's a polynomial in h, right? And so when I multiply a polynomial in h by h, well, I know that the limit as h goes to 0, it's a polynomial, so it's continuous. I can just plug in the value. If I plug in 0 for h, I just get 0. So this whole thing goes to 0 as h goes to 0, because this is a polynomial multiplied by it, and I know it's continuous. And thus, this whole limit, this whole term goes to 0, and we're just left with the n times x to the n minus 1 here. Okay, and that's what we were trying to prove, right? We wanted to show that that limit was exactly n times x to the n minus 1. So this is the power rule. When you take the derivative of a power, you drop the power by 1. You pull the coefficient out first, so you get this n coefficient times x to the n minus 1. Okay, and yeah, that's a cool little proof of the power rule. Any questions in the chat? A little bit too many markers here. Okay, so that was the first rule, power rule. Now second rule, I'll probably just combine these two. So we're gonna have two theorems, basically. Or actually, let me get a new marker. And these two theorems are going to be about the derivative of a constant multiple of a function, and if you add two functions together that are differentiable, what's the derivative of the sum of the two functions? Right, so first theorem, that the derivative of a constant times a function is just the constant times the derivative of the function. So sometimes you'll see this property as like you can pull constants out of the derivative, right? Or some people, you'll hear it referred to as that way, like you can pull the constant out of the derivative. That's just referring to this rule. So why is this rule true? Well, it's very simple to prove. You just need to write out the definition again, just like the last derivative rules. So all these derivative rules basically just follow directly from the definition. So the definition says, again, this is the limit as h goes to 0, c times f of x plus h minus c times f of x, all divided by h. Well, by definition, this is the derivative. And I have a c over here, a c over here. I can pull the c's out of the top. This is really just c times the limit. H goes to 0. F of x plus h minus f of x divided by h. And therefore, this is c times the derivative. That's what we wanted to prove. So just one step, really. QED, right? So we write out the definition of derivative for the c times f of x function. We get c times f of x plus h minus c times f of x divided by h. We pull the c out, and then we notice that this is just c times the definition of the limit of f at x. So that's the bottom here, and that's exactly what we wanted to show. So derivative of a constant times a function is a constant, and this is true for any real number. For any c in the set of real numbers here, if you can't read that. So for any real number constant, we can scale a function and we get a new function. The derivative of that new function is just c times the derivative of the function before we did the scaling. Okay, and then like I said, so we can scale functions. We can also add them together to get new functions. These are the two main ways we can get new differentiable functions. And actually, we'll see that differentiable functions form a vector space over the real numbers. So we can scale functions, we get new differentiable functions, and we can take differentiable functions and add them together, and we get new differentiable functions, which are the sum, right? So any scalar multiple, any sum, that actually makes differentiable functions a vector space. So this is like some slightly more advanced notion than a group. You have a group that's abelian, and you have also scalar multiplication on top of that that respects the group operation in some sense. So scalar multiplication is a group homomorphism, and that's actually the property that you require for it. So scalar multiple of a function is differentiable. If I add two functions, this is the next theorem, derivative rule. The derivative of a sum of two functions is the sum of the derivatives. Okay. And again, this is very useful because if you know the derivatives of the individual functions, but maybe you didn't, maybe you weren't sure about the sum, well, after this theorem, you're very sure about the sum. You know that if you know the individual derivatives and you want to know the derivative of the sum, you just split the derivative in some sense, quote unquote, split it, or you just take the derivatives of them individually and then you just add them together at the end once you take each one separately. Okay, and again, the proof is simple. Actually, this one I'm probably not going to even write out, or I'll just write the first step, but you'll see how easy it is to prove it, just like the last two theorems. Limit as h goes to 0, f of x plus h plus g of x plus h minus the sum or minus f minus g, all divided by h. Right, well, you can split this separately, right? You can pull the f minus f here, f of x plus h here, minus f of x here. You can pull that over, divided by h, and separate this into two fractions. And if you separate the f's from the g's, you'll see that the first fraction is the derivative of f, and you're going to be adding the derivative of g, and you're just going to separate this into two terms. First term is going to be derivative of f at x. Second term is going to be the derivative of g at x, and yeah, so then you'll just get that this is the sum. So this is going to be derivative of f at x. Sometimes it's written with this little caret here, this little dash, f prime x plus g prime x. So I didn't really write it fully out, but like I said, pretty simple. It just follows straight from the definitions. You just need to figure out your fraction rules so you can split this fraction into two fractions and show that each fraction is, the first one is the derivative of f, and the second one is the derivative of g. Okay, so that is our main derivative rules. We have scalar multiplication. That preserves, in some sense, the derivative. So if you have a function that's differentiable and you take a scalar multiple of it, you can be guaranteed that that new function is also differentiable. Same with the sum of two functions. If each one is differentiable individually and you add them together, now we know that the sum is differentiable. And like I was saying before, that makes our space of all differentiable functions over some domain actually a vector space. So that's a very important notion, and this shows up in like topology. You can actually use this vector space. Sometimes it'll be the tangent space to some manifold. You have like a donut with a hole in the middle. You can look at the tangent space as well, which is all of the tangent vectors at each point of a manifold. And there's some topological stuff you can do. You can calculate from that Chern character, Chern numbers, all of these homological algebra type results. You get that from derivatives. And the fact that it's a vector space, all of these properties are used to calculate different things, like the dimension for the tangent space is always equal to the dimension of the manifold, and you have as many independent tangent vectors as the dimension. So yeah, so let me just write real quick result that if you're taking notes and you're interested in like maybe higher mathematics or something like that, this would be up your alley to research more. And probably next time we'll actually, not next time, but the next main topic will be linear algebra, which is the study of these vector spaces. So let's just write really briefly, really quickly in our notes that because our space is closed under scalar multiplication and sums, like we just proved in the last theorems, we actually get, let's note that differentiable functions form a vector space over the real numbers. So usually we'll write the field. You can have a vector space over any arbitrary field. We'll usually write the field as f. Maybe I should have wrote f equals r, but this is the set of real numbers. And a vector space over real numbers means that we can add things together and we can multiply by real numbers, and we somehow stay within the space, like when we were talking about groups. And this just says that if f and g are two differentiable functions, diffable, if f and g are differentiable functions and c is a real number, c is in the set of real numbers, then that means that c times f of x plus g of x is also differentiable. Right, and that's what makes something a vector space. You can scalar multiply a function, you can add another differentiable function, and the result is also differentiable. So you have this vector space structure, you have addition, you have scalar multiplication. But the only thing here is that the functions, there's a large space of these functions because it's actually infinite dimensional. In fact, we can find infinitely many linearly independent vectors, which are just the x to the n's. So if you take 1, x, x squared, x cubed, x to the fourth, you go on forever, you can actually show in this vector space that those vectors are independent, and so that actually means that the vector space is infinite dimensional. And so it's a little bit hard to describe what the space is, but you could kind of imagine that because the space of all differentiable functions, there's like a lot of possible differentiable functions, right? We've already talked about polynomials, but we also have exponential functions, logarithmic functions, sine, cosine, all of the trigonometric functions, right? So there's a large space of differentiable functions. In fact, we'll show later once we get into Taylor series, maybe this will be way later video, but any Taylor series is also infinitely differentiable, and there's uncountably many different Taylor series you can come up with. So this vector space is very large, right? Usually we like to deal with finite dimensional vector spaces. They're somehow easier to understand. They have a finite basis. You can write matrices for the linear transformations between vector spaces if they're finite dimensional, and so on. All right, so I don't want to spend too much time, but vector spaces are very important for higher math. A lot of topology stuff and calculations involve vector spaces or modules over some ring. But usually it's a field, and when you're talking about these differentiable functions, it's usually going to be the field of real numbers, right, or complex numbers. Sometimes you have complex differentiable functions, and there'll be vector spaces over the complex numbers. Okay, so that's all about that. That's my lecture on vector spaces. No, we're still talking about calculus, right? So I'm going to do a problem real quick. This is just going to be to touch base, make sure all the rules we were just talking about, how would you apply those? I'm just going to make that very explicit for you here. Okay, and this is page 181 in the Stewart book. I have the Stony Brook edition, but any Stewart book will be good. You might need to fix the page number possibly, but this is page 181 in my book. Number 29 is one of the red highlighted ones. I think that's the ones they have the solutions for in the back. So they give us a function which is y equals x to the fourth plus 2 e to the x. And they give us a point on the curve, and they ask us what's the equation of the tangent line. So the line that passes through just that one point is tangent to it. And the normal line, which is just going to be perpendicular to that line, at a particular point. So it's at the point 0, 2. And sometimes it's a little bit of a sanity check. You just want to plug in 0 into your function and see that you actually do get 2. Or else this point won't be on the curve, and that would be weird. But if you plug in 0 to the fourth is 0, 2 times e to the 0 is 1, so this is just 2, so 0, 2 is good. So to find the tangent line, we want to take the derivative. We have the sum of two functions. We just said that we had the power rule for x to the fourth, so we know what the derivative of that is. We didn't talk about e to the x, but the book actually, I don't even think they proved this. They kind of just, it's almost the definition there's equivalent definitions, but one of the definitions is that e to the x is the function whose its own derivative. So the derivative of e to the x is just e to the x, and we'll use that here. So it's a scalar multiple of e to the x, so we're going to know how to take the derivative. In particular, the derivative of this function is, well, we can split it. It's the sum of the derivatives, and the derivative of the first function is 4x to the third using the power rule, which we just proved. And then the derivative of the second one is a scalar multiple of e to the x. E to the x has derivative itself, so this is just 2 times e to the x, which is the derivative of itself. And now to find the tangent line, we just need to plug in the x value to get the slope of the tangent line, which is y prime, the derivative of y. So at x equals 0, y prime is equal to 2 also. And so that tells us that the slope of the tangent line at this point is 2. Now we just need to figure out what is the equation of the tangent line. Well, we know what the slope is. We know what the point that it goes through. You can look up point slope form if you don't know that, but it's basically just y minus the y value is equal to the slope times x minus the x value. So this is our equation of our tangent line. It has the slope equal to the derivative at the point, which is 2. And it goes through the point, which is x value has 0, y value has 2. And now for the normal line, it's basically the same line, except the slope is going to be the negative reciprocal. So it's going to be, this will be the normal. Right, so this is tangent line at this point. The slope is 2, the point is 0, 2. Here the normal line is going to be the same, it's going to go through the same point, but the slope is going to be the negative reciprocal of 2. So it's going to be y minus 2 equal to negative 1/2 x minus 0. And this is our normal line. Okay, so basically they are the same line, they're almost the same line, they go through the same point, but the slope on this line for the tangent line is equal to the derivative, it's just 2. And the slope for the normal line, the slope is negative 1/2. It's the negative reciprocal of 2. So 2 is like 2 over 1. The negative reciprocal is negative 1 over 2. I don't want to go too much into why that's the normal line, but you can look up in the book if you're confused, or look up online, y is the slope of the normal line, the negative reciprocal of, the other slope. Of course, if you take negative reciprocal twice, you go back to the self, right? So the normal line to the normal line is the tangent line. They go kind of back and forth between the two when you do the negative reciprocal. Okay, so tangent line, equation of the tangent line, equation of the normal line. So that solves problem 29. And we found the derivative by taking the derivatives of these individually. We used our sum rule to split the derivative. We used our power rule to take the first derivative, and then we used our scalar multiplication rule. So this actually uses all 3 rules in the same problem, which you'll notice that you'll have to use these rules multiple times sometimes. Like for chain rule later, we'll probably do this next time. Chain rule is for a composition of functions you want to take the derivative of. But you might have like f composed g composed h, and then you want to take the derivative of the whole thing. So sometimes you'll have to apply these rules multiple times in the same function to get the derivative. That's just something you can't avoid. Of course, you can make these problems as complicated as you want by sine composed with cosine composed with e to the x composed with sine composed with x squared. You can of course combine these forever and make the problem more and more complicated, but I don't think, at some point you're not really testing your knowledge, right? You're just testing how quickly you can solve these derivative problems, right? Excuse me. Okay, so that was 29. Let's go to 36. 36 is on the same page, so 181. Problem 36. Okay, so problem 36, which is like a couple problems later. And this is a problem about comparing the graphs of a function and its derivative. So it asks compare graphs of f and f prime, the derivative function of f. And they give us a function, so f of x is equal to x plus 1 over x. And of course, here, so we didn't prove it for negative exponents, but 1 over x you can actually write as x to the negative 1, and you can show that the derivative still follows the power rule. So we technically only proved the power rule for integer values of n, and only if the integer is non-negative. But there is actually a fact, you can prove it more generally for any n, as long as n, I believe, is not, no, actually, no, it works for any n. So the power rule works for any n. So x to the n, the derivative is still n times x to the n minus 1, but in this case, n can be negative 1. So we have x to the 1 here, and here is x to the negative 1. So if we want to take the derivative of a sum is the sum of the derivatives, so the derivative of the first function x is just 1. The derivative of x to the minus 1 is, I pull down the n, which is minus 1, times x to the negative 1 minus 1, which is negative 2. Or in other words, this is 1 minus 1 over x squared. Okay, so now we have our function, x plus 1 over x, or x plus x to the negative 1. We found the derivative using the power rules and sum rules. So we said that the derivative was the sum of the derivatives, and each one, the first one had derivative 1, second one had derivative negative 1 over x squared. So the full derivative is just 1 minus 1 over x squared. And so now I'm going to graph these two. We're going to do a little quick sketch, nothing too fancy, but what we're paying attention to is the relationship between f and how it's, increasing or decreasing for different values of f prime. Right, because the derivative is telling you which direction the function is traveling in. So if the derivative is it's positive for some values, then becomes negative all of a sudden, usually that's a maximum. So you'll have a function that's going up, positive derivative, and then all of a sudden it turns to negative, starts going down, like an upside down parabola. But yeah, sorry to confuse you a little bit too much, but so let's try to draw f and f prime, and then I'll comment about what we're supposed to notice about these two functions. I'll rewrite the functions above the graphs, but let's compare the graphs of these two functions. So on the left, we have f, x plus 1 over x. And I'm just going to put a dashed line here. This is actually an asymptote of the function. It's not part of the function. I just makes it drawing it easier. So it will look something like this, where this line is getting closer and closer to the dashed line. And the bottom part is basically just a reflection of this. Okay, so here's our function f, and then our derivative. Line between them. So here's our derivative that we just calculated. It was 1 minus 1 over x squared. And so what does the derivative look like if you graph it? Well, as x gets very large in either the positive or negative direction, you have this horizontal asymptote, basically, which is at 1, right? Very large values, this number is really close to 1. Very large negative values, this number is also very close to 1. So let me just draw that asymptote. Right here, the line y equals 1, and then we're going to have something that looks like it's going to explode at 0 to negative, very, very large negative numbers. And similarly, it's going to come up from negative infinity on the right. And you'll notice that it crosses here at x equals negative 1 and x equals 1. Those are zeros of the derivative. And we'll study this later, but the zeros of the derivative, those are critical points. Those are points where possibly the function has a maximum or minimum. And you can look over at the function on the left. This is the derivative, remember. When the derivative is 0, those are critical points. Those are points that may be minimums or maximums. And here you can actually see that we do have a minimum at the first point, or sorry, a maximum at the first point, and we have a minimum at the second point here. And you can see that that's true here because the function is increasing to the left of, or sorry, let me start on the left point first. This point right here. The function is increasing to the left of this point, and it's decreasing to the right of this point because the derivative goes from positive to negative at this point. And you can see that in the graph here because the function is increasing to the left of this point. Then it starts decreasing to negative infinity after the point, and that leaves us with a local maximum right there. It's not a global maximum because it's only a maximum for points that are very close to this point. Same with over here, the derivative is negative to the left of the point, which means it's decreasing, and the derivative is positive to the right of the point, which means the function is going down, and then it starts going up, which means we have a local minimum here. And yeah, that's a very common theme for some of these problems. It will ask you, it'll give you a function and it'll ask you find the derivative, find the critical points. For each critical point, you're going to determine, is this a local minimum, is it a local maximum, is it a global minimum, is it a global maximum, or is it none of these things? Maybe it's just a saddle point and it's not a minimum or maximum. Okay, so this, like I was saying, these are very common types of problems that you'll encounter. This was number 36. We have the graph of f, we have the graph of f prime, and we're comparing the two and looking at critical points. I don't think they talk about critical points in this section of Stewart yet, but that's one of the important parts of differential calculus. When the derivative is 0, that's a red flag. That tells you something's going on at this point. It has either it's a saddle point, it's a local minimum, or a local maximum. But if the derivative is 0, we definitely have to check that point. It could be a minimum, it could be a maximum. If the derivative exists and there is a minimum or maximum there, the derivative has to be 0. So that's the thing that you're checking. But that doesn't always go the other direction, meaning that just because the derivative is 0 doesn't necessarily mean that it's a local minimum or maximum. You could actually have the function like x cubed, where at 0 the derivative is 0, but it's not really a minimum or maximum because it has that like saddle point where it's going up, it rests for a second, then starts going up again. But yeah, just look at x cubed. Look at the graph of x cubed if you want an example of a function that has a critical point that's not a minimum, a local minimum or maximum. Okay, so that was 36, and now I'm gonna go through a couple more rules real quick, get them all out of the way. This is a product rule, quotient rule, and chain rule. I'm just gonna throw a chain rule in there because we're not really gonna do much with it this time. I think we'll probably get into it next time, but chain rule is, one of your main computational tools to solve a lot of these problems, as well as product rule and quotient rule. So let's get those written out. Okay, so product, quotient, and chain rules. Okay, product quotient and chain rules. So let's, again, you can prove these from definition. I'm just going to write them out here, and then we're going to use them on a problem later. I don't want to have to prove each one. It's just going to be a lot of like the proofs earlier, where you're going to write out the definition using the limit, and you're going to do some sort of algebraic adjustment until you get the result, which is what we will be writing. What we'll be writing here in a second. So you can kind of see how you would solve it. You just kind of have to rewrite everything that I'm about to write in terms of the definition using limits and do some sort of algebra like I was saying. So the derivative of a product of functions this, when we had the product of two functions and we wanted to know what the limit of the product was, then we could just multiply the two. This is slightly more complicated. You can't just, and this is important, you can't just multiply the derivatives. So when we had a constant multiple or a constant scalar multiple of a function, you could just pull the constant out. Here, when you have a product of f times g and you want to take the derivative, it's definitely not, so put in your notes here, it's not the derivative of f times the derivative of g. So it doesn't break in the simple way that you would maybe expect it would. So that is like, common mistake. Don't do that. The derivative of the product is not the product of the derivatives, even though the limit laws do work that way. So here, it's a little bit different. It's the derivative of f times g without a derivative. So this is important. This is not part of the derivative. So it's just derivative of f times g plus f without a derivative times the derivative of g. And this is a g here at the end. So another way to write this, I'll write this again another way. I don't like this d over dx notation. I think it's a little clunky. So another way to write this would be f prime of x times g plus f of x times g prime of x. Or, derivative of the first times the second plus the first times the derivative of the second. So it's very important that you don't put a derivative on the g here and that you don't put a derivative on the f here, right? Otherwise the formula is just not correct, right? But if you write it out this way, where it's the sum of these two, one where you're only taking the derivative on one of them each time, that is the correct formula. And this is the derivative of the product. So you can see that the derivative of the product of f times g is not just f prime g prime, like you might expect. It's f prime g plus f g prime. And then we have two more formulas. One, so this was for the product of two functions. You want to know the derivative of the product of two functions. Now you can do it. You might be asking, okay, well, what if it's f of x divided by g of x? Okay, well, we have a different formula for that. It's called the quotient rule. So this is for the product of two functions. If I want to divide two functions and I want to take the derivative, well, first of all, the bottom function can't be 0. I can't divide by 0, but as long as that's okay, as long as I'm not dividing by 0, then the division makes sense, and we can find the derivative of the, so d dx of f of x divided by g of x. And again, I'm going to switch to the f prime g prime notation because I don't want to have to write this d over dx each time. It's kind of annoying. So this one, so the way I remember this, it's very similar to the product rule, except you have a minus sign between them, and then you divide by the bottom function squared. So other than that, it's the same. So it's f prime g minus, instead of plus, f g prime, and then you're going to divide by g squared. So that's how I remember this quotient rule. And of course, the function g can't be 0, or else this derivative is going to not be defined either. So if the function's not defined, then the derivative is not defined, of course. That makes sense. So as long as g of x is not 0, this makes sense. If g of x is 0, you can still define this function just on a smaller domain, right? You can define it on all the values where g of x is not equal to 0, and then g of x is not equal to 0, and then this formula still gives you the derivative, at least at the points where the f divided by g is defined. Okay, and then the last formula, so we've almost done everything you could possibly do with functions, right? We've multiplied them by scalars, we've added them together, we've multiplied two different functions together where neither one was a scalar. Now we've divided functions where neither one was a scalar. They could be arbitrary functions, and we can take the derivative. So what's the very last thing we could possibly do with two different functions? Right, we've done all these different things. Well, we can compose them together, of course, right? That's something we've talked about in group theory. If we have two functions, f and g, I can plug in the output of one function into the input of the other function, and I get a new function. And the chain rule says that if I want to take the derivative of this composition, that there's a formula for it as long as I have the derivatives of the individual functions. And that formula is the following. So this is one of your most popular formulas in calculus. This is called the chain rule, or chain formula for the derivative. And right, it's a chain because once you have a composition, it's going to chain in a certain way, as you'll see from the formula. So the chain formula says that if I have the derivative of the composition f of g of x, right, so I have one function that I'm plugging in as the input of another function. You'll see this in the next example that we do, like what types of functions what these look like, right? If you've never seen that, it might be a little confusing to see f of g of x. But this could be like, the square root of sine of x or something. Then the inside function would be sine of x, f of x would be square root of x, and the composition of the two would be like the square root of the sine of x or something. So this formula is going to help you calculate those types of derivatives. Derivatives whenever you have a composition of two functions, and the derivative of the individual functions. So derivative of the composition is derivative of f, and you plug in g of x, and then you're going to multiply by the derivative of g. Right, so this is like the product of two numbers. First one is I take g of x and I just plug it into f prime. I don't do anything to g, and then on the outside I get a multiple of g prime of x. Again, you could write the definitions of f prime, g prime, the x plus h, write out the limit, and show that these two limits are actually equal to each other. It's just a bunch of algebra. You just want to separate stuff out, and then you get product of two things, and you show that those two things are these. So it's not too hard. I just want to skip it for time's sake, and I think the application of it is probably more important for anybody that's watching this than the proof, potentially. So we're going to do one exercise that involves composition, and we're going to try to find the derivative. Also, it involves some of these trigonometric functions, and I've skipped over a little bit of those, so I'm going to sort of introduce derivative of sine and cosine as well. Trying not to do too much all at once, but I don't want to have to go through all the trig functions individually. So if you're confused about trig, maybe you never took pre-calc or something, that would definitely be something you might want to email me about if you need tutoring, help with trigonometric functions and derivatives of those. But we're going to use that for this problem. I'm kind of just going to explain it as we go. Okay, so this problem is page 205, same book. Page 205, number 33. And let's see, so basically they give us a derivative, or they give us a function. Right over here. And they write it as cotangent squared of sine of theta. All right, so this is actually, like I was saying, you might need to apply these rules more than once. This is actually the composition of three functions, because we're taking sine and we're plugging it into cotangent of x, and then we're taking that and we're squaring it. So it's actually composition of sine theta, cotangent theta, and I guess theta squared in some sense, and we're composing these three functions, right? Here I'm just going to write some of the things that we're using to solve this. So the derivative of sine theta is cosine theta. These are your standard trig functions, and the derivative of cosine theta is negative sine theta. And you get this sort of repeating pattern, because if you take the derivative of sine, you get cosine. You take the derivative of cosine, you get negative sine. Then when you take the derivative of negative sine, you get negative cosine. You take the derivative of negative cosine, you go back to sine. So there's this, it actually takes 4 cycles to get through, to get back to the same thing. But yeah, actually if you take the derivative twice, you get the same function, but the negative of it. So like the second derivative of sine is negative sine. Second derivative of cosine is negative cosine. But yeah, so we have our function here, y equals cotangent squared of sine of theta, and we want to solve this derivative. Right, and then so cotangent squared, let's first find the derivative of this. And of course we're going to use the chain rule, because this is a composition of sine theta and cosine squared, cotangent squared theta. Cotangent squared can be rewritten as cosine squared over sine squared. And then we can actually use quotient rule. So actually, I mean, theoretically you could just look up this derivative, right? I'm kind of weird, so I want to prove everything for you guys. I want to write everything out. Cotangent squared, I'm sure they have the derivative somewhere in the book, but here we're just going to prove it using the quotient rule, because we have cosine squared, sine squared. We know those are differentiable. So we have the ratio of the two, that has a derivative. In particular, the formula said that it was the top function derivative times the bottom function minus the top function times the derivative of the bottom function. So it was f prime g minus f g prime divided by g squared. That's our quotient formula. Also, we have x squared here, so I can actually do the power rule too. So this is 2 times cotangent theta times the derivative of the inside, which is the quotient rule. So times, and we actually get negative sine squared minus cosine squared, which is actually just minus 1 over sine squared. Which we can also call 1 over sine squared. That's just cosecant squared. This is just, by definition, basically, cosecant squared is 1 over sine squared. So this whole thing, you can actually restate this as 2 times cotangent times negative 1 cosecant squared. And so now we're basically almost done. So we have the derivative of cotangent squared. We know what the derivative of sine is. It's cosine. And so now we can put everything together. And we can finally say that the derivative of this function, we can use the chain rule. We know what the derivative of cotangent squared is. We know what the derivative of sine is. So now we can give you the derivative of the composition, which is going to be this. But then we're going to plug in sine theta for theta. And then we're going to multiply by the derivative of sine theta at the end by the chain rule, because the chain rule says that we do f prime of g times g prime. So it's going to be the derivative of cotangent squared. We're going to plug in sine theta into that, and then we're going to multiply by cosine of theta at the end. This is the derivative of cotangent squared, so it's just negative 2 cotangent of sine theta times cosecant squared of sine theta. Oh, wait, and then I need to multiply by cosine, of course. Ran out of room here. All right, let me rewrite this. So it's neat. Actually, let me rewrite what we're actually doing here. So we're using the chain rule. Chain rule says that it's f prime of g times g prime. We just found the derivative of f. We found f prime, which was this. And we know what g is, so we know what the derivative of g is, which is cosine. So y prime is actually just 2 cotangent of sine theta times cosecant squared of sine theta times cosine theta. There we go. Okay, so the first part is f prime g, and then g prime is just cosine theta here. Use 2 different colors. Okay, and that's how you do these chain rule problems. You're going to use the chain rule f prime of g times g prime. You're going to separate your function into a composition of 2 functions. Find the derivative of f, find the derivative of g. In this case, we didn't need to do any calculation because the derivative of sine is just cosine. Then you take the first function, you plug in the composition function. So we got the derivative of the first function. We plugged in sine theta here, as you can see. And then on the right with the red underline here, cosine theta is just the derivative of the inside function, which is sine theta. Derivative of sine theta is cosine theta. So that's how we get this derivative. And you can check this on like Wolfram or some algebraic derivative software, and you'll see that this is correct. A lot of these problems are a little annoying though, because as you can see when we were doing this problem, there was multiple different ways of writing this. If I'm grading your paper, I'm probably gonna, if you leave it as cotangent and sine and you don't convert it into cosecant squared or something, I'm not gonna take off points. But of course, your professor at your university or wherever you're taking calculus, or if you're in high school, they might care. They even might want you to memorize what is the derivative of cotangent squared, something like that. Once you get to integrals and antiderivatives, it might be useful to know or memorize the derivative of cotangent squared, that you automatically know it's 2 cotangent times negative secant squared. See, I probably wouldn't even memorize this on my own unless I was taking the class or something, right? But you do have to be careful that there's a lot of trigonometric relations between these trigonometric functions, and so that what that means in the end is that sometimes there's multiple different ways of writing the answer that are all technically correct. Actually at the beginning here, I kind of skipped over this, but this -1, how does this get here? You actually have a negative sine squared plus cosine squared on the top, but then we use the relation that in trigonometry, sine squared plus cosine squared is 1, so this thing on the top just becomes -1, for instance. Right, so if you didn't apply that simplification, then of course your answer is going to look different, but it will technically be correct as long as you follow the chain rule. But yeah, so all of that to just say, be careful in your class if you're taking this, because you may need to fully simplify everything, and yeah, just be a little careful. All right, I don't see any questions in the chat, so I'll just end it here. I think that was like an hour. Wow.